Continuing on, this is numerical response number 6 from the 2018 Chemistry 30 released diploma. The oxidation number for sulfur in each of these compounds. Lots of oxidation number questions, or numbers that can be solved by looking at the oxidation numbers or oxidation states of different elements on this particular diploma. Remember, oxygen inside these compounds, I'm going to zoom in. That'll be easier because it's a small space, but if I can include I numbers in here, then it's all in one place. Oxygen inside of a compound that's not a peroxide or elemental oxygen has a -2 oxidation state. There's 2 oxygens, that's overall -4. This is a neutral compound. All of these are neutral compounds, which means that the oxidation numbers have to add up to be 0. So the sulfur here has to have a +4 oxidation state. These are written as plus or minus, so this happens to be +4, but that doesn't matter for when you're putting in this numerical response answer. Sulfur trioxide will solve the exact same way, where overall it's a -6 oxidation state from our 3 oxygens, which means that the sulfur needs to have a +6 oxidation state. And then we're going to look at our sulfurous acid. We're going to do the oxygens and the hydrogens first. So our oxygens, we've got 3 of them, that's -6 overall. Hydrogens, we have 2 of them, that's +2 overall, which means that this sulfur has to have a +4 in order for all of these oxidation states to cancel out, because this is a neutral compound. And then our sulfuric acid is going to be, we have -8 from our oxygens, and then +2 from our 2 hydrogens, which means that our sulfur has a +6 oxidation number. Here's our answer here, 4646. This also nicely illustrates that the hydrogen takes precedence over the sulfur for assigning the positive oxidation numbers, because this is SO3, but then in here, this sulfite, this SO3 2-, the oxidation, it's got the same +4 as the sulfur dioxide, rather than this +6, even though it looks similar having the SO3 and the SO3. Moving on. This incomplete half reaction must be completed and balanced for it to represent the half reaction of bromine in an acidic solution. Now in Chem 30, we mostly balance half reactions using an acidic environment, but basically what that means is that we can add hydrogen ions and water molecules to balance. Which of the following rows identifies the lowest whole number coefficients for the water and the hydrogen ions that are required to complete and balance the half reaction above? This is our half reaction where we're going from bromine to this bromate ion. All right, we're going to balance this half reaction. I will do it just on the side here so we can still see our original reaction. I'm going to do this by writing out. Actually, you know what? I'm just going to do it inside this box for this original half reaction here. What I'm going to balance first is my bromines. I'm going to balance the actual compound that is changing its oxidation state. Bromine here, we've got 2 bromines. I need to get 2 bromines on this side. So I'm going to put a coefficient of 2 in front of this bromate ion, which means now I have 2 bromines and I have 6 oxygens. I'm going to balance oxygens by adding water molecules. I've got 6 oxygens on this side. Each water molecule could bring an oxygen with it. So I will add 6 water molecules on my reactant side. Now I'm going to balance hydrogen ions. I'm going to add hydrogen ions, to balance hydrogens. I've got 6 water molecules on my reactant side. 6 times 2 is 12 hydrogen ions. So I'll put 12 hydrogen ions on my product side. So now all of my elements are balanced. 2 bromines, 6 oxygens, 12 hydrogens. Now I'm going to add electrons to balance charge. They don't ask me how many electrons are transferred in this half reaction, but this is good practice in case a question did come up that asked you how many electrons does each bromine gain or lose, or something to that effect. We're going to balance charge. On our reactant side, we have an overall charge of 0. Neither of these compounds, neither this compound or this molecule, are charged in any way. And on my product side, each bromate has a -1 charge and each hydrogen ion has a +1 charge, which means that we have an overall positive charge of 10 because we have -2 and we have +12. And so in order to make our charges equal, we'll have to add 10 electrons on to our product side. This is a useful skill because you might have to use this coefficient of 10 if you were doing calculations like a cell stoich calculation with Faraday's constant or something to that effect. But for this particular question, they're just asking for the lowest whole number coefficients for water and the hydrogen ion, which we've found is 6 waters and 12 hydrogens. So D is our answer here. If you didn't know how to approach this question and balance this question, something that's good to know about balancing half reactions is that if there's no hydrogen in our original compound that's given to us to balance this half reaction, then all of the hydrogens had to come from water. So the coefficient on the hydrogen ion should be double the coefficient on the water molecule because there's 2 hydrogens in every water and only 1 hydrogen in every hydrogen ion. So automatically, because there's no hydrogen in either bromine or our bromate anion, we can get rid of options A and C because the coefficients won't be the same on the water and the hydrogen ions. The next thing that we can look at here, well, then if you were to look at these coefficients, really D is just double B. And the reason why you might end up with B is if you forgot that there's going to be 2 bromate ions because there's 2 bromines inside of this molecule, then you would end up with B. That's why we have to balance our bromines first. Next question. Use the following information to answer questions 14 and 15. Sulfur dioxide gas in air contributes to the formation of acid rain. The concentration of sulfur dioxide gas in the air can be determined by dissolving that in water and then titrating the solution produced with a standard solution of potassium permanganate, KMnO4 aqueous. The titration reaction can be represented by the following unbalanced equation. During the titration, a student would expect to observe what? All right. Now, keep in mind, here's our reactants. One of these is our titrant, and the other one is our sample solution here. So we are going to titrate it with, this is our titrant here. I'm just going to put a little label here that this is our titrant. And then it's not asking me to balance this reaction yet. I'll have to do that for question 15. But for question 14, let's just look at what we know. Here's our reactants. Here's our titrant. And this is going to be our sample solution over here. Here's our sample. Here's our titrant. On our product side over here, we end up with the sulfate anion, the manganese 2 cation, and hydrogen ions. During the titration, a student would expect to observe what? A, an increase in acidity. B, a decrease in solution volume. C, a decrease in the electrical conductivity. D, an increase in the intensity of the purple color. Okay, in the Chem 30 data booklet, which I'll just pull up on the side here, if we go all the way to the last page, they've got the colors of a bunch of different anions, or cations, sorry. Permanganate is a deep purple color. This is an RMnO4. And manganese 2 is a pale pink in a high concentration and pretty much colorless in a low concentration. Many of you perhaps have done this titration in Chem 30. I'm just going to write here, this is our purple reactant, and this is our pale pink product. We're not going to have an increase in the intensity of the purple color as the reaction goes forward because we are losing the ion that makes that purple color. So D is incorrect. A decrease in the solution volume, well, we're adding 2 solutions together. So overall, what we're going to observe is that the sample solution goes up. Maybe they're asking a decrease in the volume inside the burette. This doesn't really make sense. We're not losing any of our solution here. A decrease in the electrical conductivity, well, ions are going to be what makes something electrically conductive. we actually have more ions on our product side than we do on our reactant side. So our reactant, the only ion that we're looking at here is our permanganate ion. And I suppose the spectator potassium ion that's also going to be present in the solution, that's also there. Those would make the solution electrically conductive. But then on our product side, we have the sulfate ion, we have these protons, we have the manganese 2+ ion, and we'll still have that potassium ion that was the spectator throughout this reaction. So if anything, we'd probably observe an increase in electrical conductivity. So C is not the correct answer because we have more ions on the product side. So how about A, an increase in acidity? Well, one of our products is protons, which means we have acidic environment. And that's on our product side, which means we're going to be making it more acidic as we go throughout this titration. So we should observe an increase in acidity. For question 15, we're going to have to balance this chemical reaction. A 150 milliliter sample of sulfur dioxide required 31.5 milliliters of 0.0100 mole per liter potassium permanganate to completely react. What's the concentration of the sulfur dioxide solution, or the concentration of sulfur dioxide in the sample? Okay, we're going to have to balance this equation so that we can do stoic. I'm going to balance it using oxidation numbers. So I'm going to assign oxidation numbers to everything, starting with our sulfur dioxide and then moving from left to right. The sulfur in our sulfur dioxide has an oxidation state of +4. The manganese within our permanganate has an oxidation state of +7 because overall it has a charge of -1. Our water, the oxidation state of hydrogen is +1. In our sulfate anion, the sulfur has an oxidation state of +6 because all of the oxygens overall have an oxidation state of -8, and this is a charged ion. +6 plus -8 gives us a -2 charge overall. Manganese 2 is just an ion, so it's got a +2 oxidation state. And then our hydrogen ions are just an ion. They have a +1 oxidation state. Hydrogen's not changing its oxidation state, neither is oxygen. On both sides of the reaction, the oxygen has a -2, and the hydrogen has a +1. So what's changing is the sulfur and the manganese. The sulfur is going from +4 to +6. So I'm going to just draw an arrow. I'm going to do this on the bottom of the reaction, that this is going to be our oxidation. So our sulfur is going from +4 to +6. So that is going to be a loss. Oops, I didn't mean to open that menu. Lose 2 electrons per sulfur. That's our oxidation half reaction. Our manganese is going from +7 to +2. So we're going to have a gain of 5 electrons. We're becoming more negative. We went from +7 to +2. Gain 5 electrons per manganese. We're going to have to balance the electrons that are transferred here. We have a gain of 5 electrons. We have a loss of 2 electrons. The lowest common multiple that we can multiply both these into is 10, which means that we're going to have to repeat our reduction reaction twice. So I'm going to put a little ×2. And we're going to have to repeat our oxidation reaction 5 times in order to make those electrons balance. We'll have to have 2 manganeses, each one gaining 5 electrons. And we're going to have 5 sulfurs, each one losing 2 electrons in order to balance that to 10 electrons transferred overall, which means we get a coefficient of 2 in front of the permanganate and a coefficient of 2 in front of the manganese 2 ion. Then we get a coefficient of 5 in front of the sulfur dioxide, and we get a coefficient of 5 in front of the sulfate. The rest of this we're going to balance using our atoms. We're going to start with the oxygens. On our product side, 5 times 4 is going to give us 20 oxygens on the product side. On the reactant side, 5 times 2 is 10 oxygens, 2 times 4 is 8 oxygens, so together these have 18 oxygens. In order to get to 20 oxygens, we need a coefficient of 2 in front of our water. Now we'll balance our hydrogens. We only have hydrogens in the water on our reactant side. We have 2 waters, which means that we have to have 4 hydrogen ions on our product side. It's a lot of work to balance these redox equations, but here is our balanced redox equation. The main reason we're doing this is so that we have our coefficients that we can use for our stoichiometric question below. All right. What we are looking for is moles of, or our concentration, of sulfur dioxide. That's what we want to end up with. We want our concentration of sulfur dioxide. What we have been given is our concentration of potassium permanganate and our volume of potassium permanganate. So I'm going to start with what we've been given. What we've been given is our volume of potassium permanganate. I'm going to do this all in one step. So I'm going to show you working through it. We don't really care about the potassium here because our reaction just uses the permanganate, but there's only one permanganate per potassium permanganate, so we don't actually have to change this concentration at all if we just go to pure permanganate. So we have 0.0100 moles of permanganate per liter. Now, we are going to turn this into just moles of permanganate. Before we can do any sort of stoich of converting moles to moles, we have to just have moles. So we're going to do this by canceling out the liters with the volume that we've been given of potassium permanganate, which is 0.0315 liters. This way, my liters here are going to cancel out. I've just converted my 31.5 milliliters into liters by dividing by 1,000 or moving the decimal place 3 spots to the left. Now what I have is moles of permanganate. I want to change moles of permanganate into moles of sulfur dioxide because what I'm looking for is the concentration of sulfur dioxide. I'm going to do that by multiplying by what I want on the top, which is moles of sulfur dioxide, and what I already have on the bottom, which is moles of permanganate. Now you'll see that I have moles of permanganate in the denominator, moles of permanganate in the numerator, so those cancel out. The numbers I put for this ratio are the coefficients from my balanced chemical equation. That's why we had to balance this. It is a 5:2 ratio. 5 moles of sulfur dioxide for every 2 moles of permanganate. Now what I'll have as far as my units is moles of sulfur dioxide, but I don't really want moles of sulfur dioxide, I want concentration, which is going to be in moles per liter. So the last thing I'm going to do is multiply by 1 over my volume so that I get liters in the denominator, and I have 0.150 liters of sulfur dioxide. I get that from right here. I'll highlight that in blue. That's my milliliter sample, whereas these belong to my potassium permanganate. Here's my calculator. I'll move it so that I can see all of my numbers that I put together. So I will start with my 0.0100 moles of permanganate, multiply by my volume, 0.0315. And then I'm going to multiply by my mole ratio, which is 5/2. And then I'll end by multiplying by this fraction, which would be the same thing as dividing by 0.150. What I end up with is not any of my answers, because the answers I've been given are in millimoles per liter. So it's 0.0150 0.00525. To change this to millimoles, because there's 1,000 millimoles in a mole, this is in moles per liter, so I'll just write that on the side here. This was oops, that's my highlighter still. This was 0.00525 moles per liter, and then I'd multiply it by the fact that I have 1,000 millimoles in a mole. And if I bring my calculator back, that will bring me to 5.25 millimoles per liter. That was my concentration of sulfur dioxide, which I should have written here. This was sulfur dioxide. Moles of sulfur dioxide per liter. That's the answer to question 15, C. I'm going to stop the video there, and in the next video, we'll work through our cell-based questions for redox.